point is that equation, we'll see it over and over again. So just remember D matrix times fourth derivatives of W for now, and we'll see it later on. Let's try to solve now these equations for some cases, not necessarily very simple, but of some interest to real structures. So the problem we're going to solve is this one, where I have a plate and I have a point load on one end and a distributed load on the other. And this is not just an academic exercise. It is very much related to the so-called problem of a stiffener termination. If I have a stiffened panel here, and those stiffeners, for whichever reason they terminate, but the panel, the skin panel, let's say, continues on. They would terminate if there's not enough room. They would terminate if there's some other structure that has to go through there or be located there. As soon as they terminate, that means that locally now, if I isolate the portion of the skin with a stiffener, at this end here, I would have this point load or nearly point load or concentrated load from that stiffener applied. Now I'm showing it as tension. It can be tension or compression. And at the other end, far enough from this termination, I would have the load fully distributed and transferred into the panel and being a uniform load. Now there's one slight thing here that I am omitting for now. Because the stiffener actually is loaded, let's say, along its neutral axis, then it's not simply an in-plane load here at the skin, but there's also a bending moment because of the load being eccentric. We are neglecting that, and we've done the solution. A master student has done that, so it's not that it cannot be done, but it takes a lot of algebra. Why are we doing this now? Is we're saying, okay, if I know that I'm going to have the stiffeners terminating, most likely right where the stiffener terminates, which is at this location here, the skin, if I designed it just to take the load in the distributed form, would definitely not be strong enough. So I would need to reinforce the skin, and we select obviously to reinforce the skin locally, because making the skin, the whole skin, twice or three times as thick while it would work, it adds weight. So the challenge becomes to determine over which region from the load introduction here, the concentrated load, over which region measured by a length L and width W, will the stresses coming from this concentrated load be much higher than the far field stresses, and therefore would define the region that we would need to reinforce. So this is actually now becoming useful, because after all, ultimately we're interested in a design that would work, and one of the questions we would have to ask ourselves is, okay, how big of a doubler, how big of a reinforcement do I need in terms of a length and width? In order to do that, we need to determine the stresses for this problem, and we make some assumptions. It's a homogeneous orthotropic plate. The layup is symmetric, so the B matrix is 0. That the layup is balanced, so the A16 and A26 terms are also 0. That's just for algebraic purposes to make it slightly easier. And we are assuming there's no twisting, bending, coupling. We mentioned last time, I believe, that if you have anti-symmetric layups or layups using only 0s and 90s, or I'm telling you now, layups using only fabric material, plain weave fabric preferably, then the D16 and D26 terms are 0. And we assume that the plate is sufficiently long and wide so the solution is not affected by the boundary proximity. Basically, as a first cut, we will assume this is long in this direction, so there's enough room for the stresses from the high value here to eventually go to their constant far field value, and the plate is wide enough so that whatever stress increase we have in this region will not reach the boundaries, because that would make the problem slightly more complex. These assumptions reminded me one thing I wanted to say. I keep mentioning quasi-isotropic, and just for purposes of definition, it's also in the text in the book. One way to create quasi-isotropic laminates, or the best way to create quasi-isotropic laminates, is to make sure that you have exactly the same number of fibers in every direction. But instead of having an infinite number of fibers distributed every degree, you can do it every certain intervals of degrees. So the quick way to do this is you take 180 and divide by n divided by 2. So if you have n layers, you divide it by 2, you get 4. No, you don't get 4. I haven't told you what n is. The example in my mind is 8, but don't worry about it. If you have n layers, divide by 2, and then you divide that into 180. That tells you that you need fibers every so many degrees. So if the example says n equals 8, 8 divided by 2 is 4, 180 divided by 4 is 45. So you need to start from 45, then the next one would be 0, the next one is minus 45, and the next one is 90. Basically, those are the only angles that appear in multiples of 45 that would satisfy this. So a symmetric laminate that uses these in any combination or any order would be quasi-isotropic. So 45 minus 45, 0, 90, symmetric is quasi-isotropic, but so is any permutation of these angles, 45, 0, minus 45, 90, and so on. If instead of n being 8, I had n equals 6, 6 divided by 2 is 3, 180 divided by 3 is 60. So any combination of 60 minus 60, 0 in a symmetric laminate configuration would give me a quasi-isotropic laminate. And you can change n to anything you want. It's just that after a while you will be getting fractional angles and so on. And if you're trying to think where I got this, 2 times 180 is 360. So I'm taking the full circle of going around, and I'm making sure that I divide it in equal intervals, and I have fibers in those equal intervals, which is the same. That's why where this comes from. So that was just a parenthesis because I keep mentioning quasi-isotropic, and I meant to say that's one way of creating quasi-isotropic laminates. Stress-strain equations. This is the forces, and this is the A matrix with A16 and A26 equals 0. So we get this set of equations. And if I divide by the plate thickness capital H, then nx divided by h, as we said last time, is sigma x, and this becomes sigma y, tau xy. And then all these just get divided by h. We assume that there's no dependence on the z-coordinate out of plane. Basically, it's a plane stress kind of problem, so all the derivatives with respect to z are 0. So my equilibrium equations, which had, the first one had d tau xz dz here, is not there. D tau yz dz here is not there. And the full third equation, as shown back here, where are my equilibrium equations? Here. So in these equilibrium equations, the last terms of the first two equations and the entire third one, which involves the out-of-plane stresses, disappeared. So that's what simplified things over there. So if I solve for the strains from my stress-strain equations, I get these expressions for the 3 strains. Now, my strain displacement equations, this moves up, yes. Remember, epsilon x is du dx, epsilon y is dv dy, and gamma xy is du dy plus dv dx. Now, these are 3 equations in the 2 unknowns, if you want to call them, u and v. So I can actually eliminate u and v and arrive to a single equation that will only involve epsilon x, epsilon y, and gamma xy by taking appropriate derivatives here. And you can show that, or you can find it in the book, or you can take my word for it. This is the answer. When I eliminate from these 3 equations u and v, I arrive at the classical compatibility equation that only involves the strains. But I know the strains calculated here, so I can substitute into this equation for those strains to get this, which now involves the stresses. And now I have the equilibrium equations that I just showed you at the bottom here, 2 equations. So I can eliminate 2 of the stresses in this last equation here to arrive to a single equation that will involve only 1 stress. In this case, it's the sigma x stress. X, notice this is my xy coordinate system, so x is pointing down in the plate that we have there. 4th order partial differential equation with beta and gamma as defined here. And this is one of the cases where you can solve it exactly using infinite series. The boundary conditions for the problem tell us that at this top surface here, x equals 0, my sigma x stress is 0 everywhere except for the middle point location where it will actually equal my applied force divided by the local cross-sectional area, h, the thickness of the plate, and little h, the width of the region, let's say, of the flange of the stiffener, or the width over which this load is applied. Then at the other end, I have sigma x at x equals a, which is a constant value. And then sigma y at the two vertical edges is 0, and tau xy everywhere on all the edges is 0. So I have to solve for this, and I think, yeah, let's do some of the solution, but we will stop and then we'll do the homework. Where's the little gizmo, the lug? But it took 15 minutes to do like 30. Okay, you guys had better have good answer though, because it took so much time. All right, yeah, we still have time, but keep on moving it. I assume that the solution will be some function of x times cosine n pi y over b, for reasons that will become obvious in just a little bit. If I use this and I substitute in my governing equation shown here at the bottom, then the y dependence disappears because I have even derivatives of y, so the cosines reappear, and I'm left with a single equation on x, an ordinary differential equation, fourth order on x, which from standard differential equation theory, it's in terms of exponentials with the exponents. 4 exponents, plus or minus here and plus or minus there, means that I have 4 different exponents. Now, in general, there's nothing that keeps the beta squared from being smaller than 4 gamma. So this quantity under the square root, or this quantity under the square root, could be negative. So the solution could be complex. There's nothing that keeps complex conjugates from appearing, and that means you get decaying exponentials and increasing exponentials as part of the solution. If I just take this now blindly and I combine with my expression here and recognize that this n, which appears there, it can be anything, any integer, then it becomes an infinite series. So I will have this form to represent this, plus a constant, because this constant k0 also satisfies my equation if the stress was k0, and because these are all derivatives, obviously the constant will disappear. Why do I add the constant? Because what I'm using here is what's called a Fourier cosine series, and I know from the theory of the Fourier cosine series that I need a constant to recover the average value of the stress I'm trying to approximate. Anybody that's still with me may have noticed that I said there are 4 phi values here, and I've only used 2 of them. That's because I'm making an assumption, hopefully it's on the next page. Yeah, I'm making an assumption that the plate is long enough, and therefore, if it's too long, these positive values of phi with positive real parts would actually explode, and therefore are not part of the solution. There are no infinite stresses. And I'm using only the ones, therefore, that have negative real parts, which would be 2 of them in general. If my plate is short, what do I mean by short? If the distance between this edge and that edge, or the length a, is very short, then those exponentials with the positive real parts don't have enough time to become infinite, and therefore I would need to include them. And in fact, you can play a game and keep changing the value of a and solving using all 4 exponentials, and all of a sudden you will find that after a while only 2 of them are what you need if a is too large, and you will need all 4 of them if a is too small. So for now, let's say it's long enough, and that means I will only use the 2 phi values, and I'm adding the constant k0 again from the theory of the Fourier series because I need it for reasons that will become obvious in a second. Having determined sigma x, I can then use my equilibrium equations to determine sigma y and tau xy, which this is just straight differentiations and integrations from this expression here. Notice that when I do that and I check for my boundary conditions, if y, let's look at sigma y here, if y equals 0, then I get 1 minus 1 is 0. Sigma y is 0 at y equals 0 on this edge, which it is. And if y equals b, then cosine 2n pi is again 1. 1 minus 1 is 0 again, so it's 0 at the other edge. This is the reason why these appear as even n it becomes 2n, so that both on this edge and on that edge I can satisfy the boundary conditions for sigma y. Similarly, if you take the tau xy expression and you check its values at the four edges, you will find that it's 0, so it satisfies the boundary conditions. And what I still haven't satisfied are the boundary conditions on sigma x. Basically, I haven't clearly imposed the condition that at this edge sigma x is 0 and all of a sudden jumps and then it's 0 again. To do this, it's just a direct Fourier series determining the nth or the nth term of a Fourier series. Basically, K0 is by definition of Fourier series the average of the function sigma x at any x location. And that average is just the force divided by B times h, the thickness of the plate. So this, the total force divided by BH, is the average stress, and that's what this quantity, sigma x, should be at any x location. If I make a cut along x, I should still find the same value for the average, and you can check that by integrating. You'll find that the y dependence disappears and you are left with f over bh. Now, that gives me the average, but I still have to reproduce this type of shape for the stress at x equals 0. 0 for most of the edge, and then it jumps to the applied local load and then comes back down to 0. That means you take that function, you integrate it from here to there after you multiply by cosine 2q pi y over b. Do the same thing on our Fourier series, and when you do that, you could eventually determine that this will only work if an is given by this quantity. That's standard Fourier series. If anybody is having trouble, come to my office and we can show it in detail, but basically it uses the fact that cosine 2n pi y times cosine 2q pi y will integrate to 0 unless and only unless n and q are equal, from which you will pick up only one term from this series instead of the infinite series, the one when q and n are equal, and that will give you your an. So let me stop here for now. We'll see how good the solution is next time, but I need to talk about the homework. And where's the little thing going? Okay, we still have some time to go. Let me bring up the homework now. Homework 1. Guys at the back can see this, or should I make it larger? Okay, I'll make it larger. It wasn't as enthusiastic of it's okay that you guys said so. So we have a rectangular laminate, and this is the stacking sequence: 45 minus 45, 0, symmetric, which means 45 minus 45, 0, 0 minus, 45 and 45, and that's the entire laminate. So there's 6 plies. So, and it's under pure torsion. So for those of you who thought that after the second year torsion and Prandtl stress functions you were done, I'm avenging myself on you here. And the twisting moment, mxy, or the torque T, is 44.48 Newton millimeters per millimeter. Remember, these mxy are, in classical laminar plate theory, are per unit width. So these are per millimeter width. And why the value is obscure is if you actually translate this to English units, it will be a very nice round number, but still I'm using English units because of my background. So that's the applied load. We are told that the out-of-plane deflection W for this laminate is 0 at x equals y equals 0, and that the first derivatives, dw dx and dw dy, are also 0 at the same location, both at x equals y equals 0. This means this is my rectangular laminate, x going through the center, y perpendicular here, and I have my torsional load. W is measuring deflection out of plane. You are supposed to determine the actual shape of W, so you have to tell me exactly how this deforms, and plot this W. Now, for the plot, you will assume, and only for the plot, I don't want the answer for W to include these dimensions. I want them in terms of A's and B's, and then only in the end you substitute. So the length is 10 centimeters along X, this dimension here, and the width is 5 centimeters. And if you cannot do a 3D plot, then that's okay, but I want then a plot of W as a function of Y at X equals -2, X equals 0, +2, and +4. So at different locations, you will plot exactly what the shape is as a function of Y, so I can tell that you got the right shape. Having done all this, then you go to part B. Determine the value at which the laminate fails and the type of failure. So Colibri or whatever else you want to use, you apply this load, and you have to tell me what's the maximum value MXY. So it may not be 44.48. The 44.48 is just so that when you do the plot later on, we'll have some actual shapes to compare. But find at what value of MXY you get failure, which ply fails, and in what form. Is it a transverse tension, compression, shear, or if you use more advanced failure criteria that differentiate between fibers and matrix. If you can tell me that, that's not necessary, but I would definitely will want to hear from you. It's failing because in the direction perpendicular to the fibers in compression, this ply has failed, or whatever it is. And at failure, you will tell me exactly where that is, not just the ply, but you will tell me whether it's the middle of the ply, the top of the ply, the bottom, where through the ply thickness it happens. I want the pinpoint accuracy on this one. And what is the maximum strain? Now, there are 3 strains, epsilon x, epsilon y, gamma xy. I want you to just look at the 3 strains at that location and find the one that has the highest absolute value. So if epsilon x is 10,000 and epsilon y is 3,000 and gamma xy is 3,000, the answer is 10,000 for that part. Just tell me of those, which one is the largest. Why am I doing that? Because I think when you look at it, you will observe one of them is much larger than the others, and by forcing you to observe it, then maybe you will remember that in problems of this kind, typically one of the strains, the one that you are going to report to me, is much higher than the others. Give only the highest of the 3 strains. Okay. Any questions so far on this? I give you material properties. X is parallel to the fibers for the material we are talking about. Y perpendicular. This is Poisson's ratio, shear modulus, thickness of the ply, and then tension compression parallel to the fibers, tension compression perpendicular to the fibers, and shear. Now that's classical laminar plate theory, basically, and first ply failure, and a little bit of math to give me the shape of W. Now there's one more problem, where we say, okay, we actually tested this laminate now, but we did not test it at room temperature. We tested it at the elevated temperature wet conditions. And we found that it failed at half the load that you predicted in part 1, because part 1, for one thing, includes only room temperature values, doesn't account for the fact that it's conditioned with moisture, fully saturated with moisture. So if there were no damage in the specimen, but someone told us this is an A basis specimen, so it's at the low end of the material strength, 1 percentile of the population, then you are supposed to somehow tell me what is 2 things: the coefficient of variation. Coefficient of variation is standard deviation divided by the mean. And 2, the B basis of the critical strength property, whatever is the failure mode that we said on the previous problem. If it's transverse tension, let's say I want you to calculate the coefficient of variation